system, our benchtop system. I want to go through a first 10 minutes of just theory so everyone understands the principle of X-ray diffraction, and then we'll get into running a live sample and show you how fast it is and how easy it is with our system. So what is X-ray diffraction? It is a characterization technique used to looking at the crystalline structure of a material. So what we are investigating is the atomic bonding. And in this atomic bonding, we're investigating it by striking it and diffracting off planes of diffraction using an X-ray source. This is a non-destructive technique, so whatever you put into your sample comes out the exact same way. So you can test it in multiple ways or techniques without worrying about the influence of the X-rays onto your sample. Again, what we're doing is using an X-ray source. We come in and strike a crystalline sample and diffract off of different planes inside that crystalline structure. And depending on the spacing of these crystalline structures, we get a pattern. And when we are striking material, we can think of crystalline material in three ways. Random orientation, which is ideal. That means we are representing every plane of diffraction equally that's in the sample. We have single crystal, where every plane of diffraction is lined up in one orientation. Or we have a preferred orientation, where there is some variation. It's not completely perfectly aligned, but one phase or one face of the crystalline structure is in a predominant alignment to the X-ray source and detector. So again, we're looking at a periodic arrangement in long order, which is going to give us planes of diffraction. So again, we have the atomic coordinates, and depending on which way we are striking that sample, we get a diffraction plane. So this is our 0, 1, 0, which is indicated by the Miller indices, the HKL indices of indicating what plane we're diffracting off of. And each plane will give us a different response in a different location for the peak. And what we want is long order diffraction. So we get this occurring multiple times. And the more times this occurs, the bigger the peak we see. And we can look at each of those planes of diffraction and relate that to a peak position. So this is almost like a fingerprint or a thumbprint to indicate what we are looking at. So we're not only looking at the location, but proportional to the peak, we also need to know. That's all stored into a database that we need to search. So that database is going normally at the 5 or 3 strongest peaks and at a certain proportionality. As I said, you can have what's known as preferred orientation. That's where instead of getting completely random dispersion and you're getting an equal number of strikes according to how many of those phases are represented into a sample, versus having a preferred orientation where one plane of diffraction happens to align better than the other planes. So you get an exaggerated number of diffraction peaks off of that one plane versus the rest. This is non-ideal. There's ways to mitigate this. Normally we can do sample rotation, that will do some mitigation of it, or we can do transmission where we're shooting through the sample and mitigate this, or you can even use capillary optics where you're spinning and letting the sample fall and free fall down through and getting all the possible orientations, because now you're eliminating any kind of packing issue. This is why we want to be very careful with powder samples on how hard we press the sample into the aluminum cups. If you're pressing very hard, you're going to have more preferred orientation. So normally you're just going to use a microscope slide and just press very gently and get it just even with the cup. So that eliminates some of this preferred orientation. Depending on the species, you're going to have preferred orientation. There are certain cylindrical species that are more attuned to it. Honestly, if you have a cylindrical species, they're going to want to lay down and not stand straight up. So there are inherent problems with certain crystalline structures. What we can also see in X-ray diffraction is something called amorphous. This is one that has no long-term arrangement in its atomic structure. So we want to see an arrangement that repeats over the pattern of the structure. If we get something that does not repeat, we basically get a huge amount of microdiffraction peaks in here that's going to make this big sort of hump, and that's an amorphous hump. There's still information you can get from amorphous, and most of the time you're going to get partial crystallinity and partial amorphous if you do have amorphous content. Unless if you have something like a glass. Glass is melted silica powder and it's completely amorphous and you're going to get this huge hump. Ideally, we want something that's crystalline so that it has this long arrangement and we can get good diffraction peaks out of it. But a more common one is to have a portion of amorphous content with a portion of crystallinity. And again, it is very important to know this amorphous content. Pharma, it lets us know the bioavailability. The more amorphous content you have in a pharma, the better bioavailability and ability to absorb into your bloodstream it has. The more crystalline it is, the less bioavailable it is. So it is very important in different areas to get a certain percentage of crystallinity versus amorphous. For regular powder diffraction and inorganic, you don't really want amorphous. That's not great, but you're going to get it. So again, what we do is we run a pattern. We identify what we see in the pattern. So we basically put mark the peak positions or have the software automatically do it, mark the background, and then we use a database that has a spectral library and compare that database to what we just collected. And the most common databases are the ICDD or the ICDS, or there's a free one called COD. So there are many databases available out there. And you can take that database, process it, ID it, and ID your spectrum what you have. And this can be single phase, multi-phase, and with now the newer softwares, the Rietveld softwares, you can easily quantify how much of each of those phases you have. So that's a way we can use X-ray diffraction for quantification and identification. For sample prep in X-ray diffraction, the most common way or easiest way is just a mortar and pestle. If your sample is soft enough, this is a nice way of getting down to a fine particle without actually destroying the crystallinity of your particle. The more the heavier processing you have on your particles, the more amorphous content you're going to create because you're actually destroying that crystalline product. You can use a ball mill for harder materials. This is a much more ideal compared to something like a ring and puck. A ring and puck mill is designed to actually destroy the crystalline phase because you're trying to get rid of that component in X-ray fluorescence. So it's ideal for X-ray fluorescence, terrible for X-ray diffraction. So a ball mill, which is just based on impact shaking and grinding, is ideal for this type of technique. You can also use what's called a micronizing mill. Now this can get down to less than 1 micron and still keep the crystalline structure. The issue with this mill is it is expensive and time consuming to clean. You have about 50 different little cylindrical spheres in here, and you have to take it apart and clean each one of those out between sample to sample. Ideal for research, awful for QA/QC. Again, for sample prep, we normally just use a microscope slide and put the sample into it, and we want to keep the powder even with the outside edge. That gives us our height from X-ray tube, the sample, to detector. Shifting that height, we'll actually see a shift in the peak positions. So it's very important we keep that height very exact. So this is a correctly prepared sample where you can see it's nice and even. This is an overpacked sample. And what we see, not only a shift in the peak positioning, you see your background going up and you see scatter. So it's a lot of issues because now you're actually shooting through some of the sample. So it is very important that you do get good sample prep for X-ray diffraction. You can do transmission. And in transmission, you're basically putting your sample, screwing 2 Kapton windows so it's X-ray transparent. And instead of doing a reflection off the surface, you're transmitting through the sample. This works very nice for organic materials. For anything more dense, inorganic material, you're absorbing too much of the X-rays, so the amount of intensity you're getting out of here is almost nothing. So this is really only a technique for very light matrix materials. The benefit outside of just eliminating preferred orientation, you're always going to get better resolution with transmission versus reflection. But again, the key is you don't get nearly as much intensity because you are absorbing some of the X-rays. So you can see where you're getting much better resolution between all these peaks, but the intensity is lower. So you must count longer. And these are some of the common techniques you'd see in X-ray diffraction. Regular reflection, zero background, where you're using a cut silica at a certain angle that you get only one peak of silica out of field, and it's normally up in the 80-degree range where you don't really normally care about stuff. So you can do very small quantities, micrograms, transmission, or even capillary. That's the theory on X-ray. Let's run some samples. So right now, I have a single sample in here rotating. We have, again, is a curved position sensitive detector, X-ray tube. And in most diffraction systems, you are moving the tube and the detector. For us, we're not moving anything. Everything is simultaneous diffraction. So no moving parts other than rotation. The mouse. And you can see we get simultaneous diffraction across the entire spectrum. And right now we're at 10-second acquisition. I could stop now if I wanted to. Depends on how well the diffractor your sample is, how long you're actually going to measure your sample. The key is to get a good ratio between your peak and background. So if you have a good diffracting sample, that could be in seconds. If you have something that has a higher amorphous content or doesn't diffract so well, then you may have to go to 3 to 4 minutes of acquisition. So we're just going to do this for a 60-second acquisition. The other aspect of the time ratio is you need to know your trace element or your trace phases. If you're only looking for major and minor, again, that's going to determine your length of diffraction time. So the longer you go to a point, the better peak to the background you're going to get. And right now we're already at 2,500 counts. So normally you need about 1,000 counts for good Riedenfeld refinement. Okay, that's a 1-minute acquisition. This was a yttrium oxide that I used to actually just make sure that the system is aligned because it has peaks high and low throughout the entire spectrum that I know of. So as you can see now, we have everything in here. There was nothing I had to change. All I had to do is basically hit stop and start. The only aspect we can possibly change here is the power of the X-ray tube. This is a 50-watt microfocus source tube. So what we're doing here is a low power tube. We have, that's a sample? Yep, that's a sample, just rotating. Here, tough to do with a microphone. Let me repack it. And you can see that's just a sample powder. So again, what we have is a 50 watt tube, so it's a very low power tube. So how do we get high intensity diffraction? We're using 2 focusing mirrors. So we're using what's called a microfocus. So these mirrors actually, instead of letting all the X-rays just scatter everywhere in only a small portion striking the sample, we're focusing on all the intensity coming out of the tube and going directly onto the sample. So we're doing an analysis area of 5 millimeters by 150 microns. So it's basically a pencil length, 5 microns across the sample. And as we're rotating it, that means we're doing an area on the sample of 5 millimeters. So it's a nice little larger area, but still getting high amount of diffraction energy onto that. It's about equivalent of about 2,000 watts of a standard X-ray tube if you didn't have the mirrors on it. So this is very unique for a benchtop system to have this micro focus on it. Again, to change out any of the accessories, it's pull in, plug out. So we can put every kind of accessory on here, from sample spinning, non-spinning. Again, same sample holder for transmission and reflection, as we have a hole straight through here that we can put in a Kapton-based window. I can put a thin layer stage. So if you're looking at layer thickness and roughness, I can actually do this on a benchtop. We can do a capillary stage on this benchtop. I can do a controlled atmosphere on this. So it is a Kapton window that's sealed. You can actually take over to a glove box, prepare your sample if you need to, put it under an inert atmosphere, put it back in here. And it even has ports if you want to start changing the atmosphere and do dynamic studies. Because we are getting the entire pattern simultaneously, you can do 10-second acquisitions and then overlay them and actually watch the dynamic study through time. We can do this with a hot stage as well. So you can actually watch your transition from your phase to phase. So if you are creating a new material and you're worried that there's some intermediate phase that may be really influencing or maybe detrimental, you can actually watch and see if that phase pops up. So it's really nice for QA, QC and research on a benchtop system. There's not very many benchtops that's gonna allow you to add these type of accessories. So it's a very nice entry level, but yet has research grade accessories that you can put onto it. I'm watching the time, so let's go to questions. Here you go.
So for sample prep, does USB require not to grind, or what is it?
You're gonna have to do some grinding, since you do want to keep a nice surface on it, and you do need to get the particles down to around 100 microns. It's ideal for X-ray diffraction. So you do need to do some type of grinding. We just want to do minimum grinding, and the grinding we want to do is impact based and not shear based. Like a ring and puck is a milling system that is shear based. So it's actually designed to cut the particles instead of where a ball mill, it's using impact and breaking up particles by striking them. So you're actually breaking the crystalline structures along their planes of crystallinity. So you're keeping the crystalline intact. Where a ring and puck mill, as it's shearing, it's actually cutting those planes of diffraction and destroying the crystallinity that you're gonna see. So yeah, you're gonna most likely have to do some type of particle control. And then a lot of times, a lot of people will take a sieve and do different fractions. So they'll do a coarse fraction, fine fraction to see what the difference is. And for a lot of materials, you're gonna find your fine fraction is lower in silica and zirconium if you're doing geologies, and then your harder coarse fraction is gonna be those tougher coarse particles.
If USB requires
Not to grind? Well, you can't. I mean, yeah. If you don't want to grind, you don't have to grind. Yep. Right.
I don't know.
I don't know that exact requirement. What's required for that? But if they do require not to grind, there are still ways of not grinding. So if you do still have a solid, you can do. It's going to be a surface analysis primarily, but you can actually put in a scissor jack and lift it up for larger material. So we've had parts of solar cells put in here on a scissor jack up to because they didn't want to destroy the product. So that's absolutely a way of doing it if you don't want to grind. Now, you may want to run the sample in different orientations, so you're seeing not just one plane of diffraction, but multiple planes, so you can turn it 90 degrees and run it that way when you are doing a non-prepped sample and can't rotate it or spin it. Other questions? Yes, here you go.
Which portions are rotating on your device? Both the detector and the sample, or the detector and the tube?
Just the sample. The only thing that moves is the sample. The tube does not move, the detector does not move. So the only thing we're seeing is a sample rotation. So the geometry we're doing is what's known as asymmetric or Debye shear. So it's basically we have diffraction rings going up the whole way through the detector so that we don't have to move anything. So it's essentially, if you're familiar with a Lowy technique, you're taking Lowy, but instead of getting a pattern shown this way, you're taking that circle and just going the whole way up around it and getting the edge of the pattern up on your detector. Where you have Bragg-Botano, which is moving your theta theta or theta to theta, we're not doing that geometry. We're doing asymmetric geometry. It gives you the same results. It's just a different way of capturing diffraction patterns. You're welcome. Other questions? If you guys want, you can come up, take a look at the instrument, ask questions about the instrument, take a look at it, and we can adjourn that. I hope you found it useful. Thank you.